Hello?
Hi.
Hi, how are you?
Good. How are you?
I'm doing great.
Yeah.
Well, your camera's working. That's good.
hmm
Is there anything you want to test or?
Um. No. Let me test the sharing thing. Are you able to see my screen?
Yes.
Okay.
Yep.
Okay. Great. Great.
Were you able to attend the session this morning or?
A little bit. Yeah.
Good. I'm kind of excited that I got put in your session today.
Hmm.
It'll be fun to listen to.
Yeah. Thank you.
Mhm. I think we're good to go whenever you want to present.
Okay, I'm ready.
Okay.
I think I can begin now. Good morning, everybody. I want to thank AIM Institute for inviting me to give a talk at this Infotech event on misinformation detection using artificial intelligence. I also want to thank the sponsors for supporting this very important and timely event for the community. So let's begin. If it was an in-person meeting, then I would have shown this message to you and would have asked you how many of you think that it is true. Well, if you are a Trump supporter, then obviously you won't believe it. But if you're not a Trump supporter, some of you might incline to believe in it. Then I would have shown you another message and then would ask you the same question. How many of you think that this is true? If somebody is a diehard QAnon supporter or even a Hillary hater, then that person would incline to believe this second message as well. And be delighted, actually. So you are smart, very smart. So all of you would be able to figure out that these are fake news. This is not true. And it should be easy for you. It is indeed easy to determine whether these messages are fake or not. The point that I'm trying to make here is that if we have enough time, if we have enough resource, computational resource, fact-checking venues, and if we have limited exposure to these kind of messages, then it's not very difficult to determine what's the intention behind these messages, whether they're true or false, whether they're fake, misinformation, disinformation, and so on. The problem starts happening when fake news or misinformation is propagated through online social media. It gets viral. And pretty soon it creates a large-scale information cascade, which makes things very difficult, which makes our understanding clouded. We find it very difficult to determine the intentions behind these messages. I want to show you some tweets based on the recent COVID pandemic. And I would like to engage in a discussion with you about the intentions behind these tweets. So let's look at the first tweet. If you read the tweet, you will see that it kind of talks about a cure of the COVID disease. And well, it could be a fake cure, right? Another message, if you look at it, it doesn't talk about any cure, but it talks about the politics of COVID. It talks about some conspiracy theory. It says that COVID virus is bioweapon. It's engineered in a lab at Wuhan, China. So what is the intention behind this second tweet? Maybe it's politically motivated, or maybe it's a conspiracy theory. The third tweet is interesting because it is kind of backed by some research. It's about a cure, and the person who has sent this tweet, he or she is trying to back up her or his claim with a research paper. The fourth tweet, it asks a question. It asks a question about a cure to coronavirus, but it's kind of a funny question because it says that which essential oil is best for getting people to relax about the coronavirus. So it's not exactly about the cure for the coronavirus, it's for some relaxation. So it could be a misinformation, it could be a rhetorical question, it could be just a joke. The fourth tweet for sure is a joke because it talks about collaboration on a song as a cure for the coronavirus. The fifth tweet is ambiguous. The one that you see at the bottom, it talks about some cure, hydroxychloroquine or Z-Pak combo, and then it kind of asks a rhetorical question, right? Why are we not taking this seriously? Why are we not, thinking about it, and so on? So if you look at all these different tweets, you get to see that they have different types of intentions. There are different types of misinformation, true information. They're kind of mixed up, right? So if you spend some time, you should be able to understand that these two tweets are completely misinformation. A little bit more time, you will be able to figure out that this tweet is also misinformation. It's also fake news. But what about these three tweets? How would you categorize these three tweets? Are these misinformation? Are these tweets trying to convey misinformation? What kind of misinformation? What are the intentions behind these tweets? Are these jokes? Are these satires? Are these mockery? We don't know. And it's hard to tell. So when you are overloaded with information, then it's very difficult to determine whether it's a misinformation or a disinformation. If you, for instance, look at the difference between misinformation and disinformation, you will see that both misinformation and disinformation convey some false or misleading information. But the fact that the misinformations are not created for causing harm to people or society, but there is a malicious intentions behind disinformation. These are deliberately created to cause harm to people or society or to country, right? So we understand the difference between misinformation and disinformation, but then when we focus on misinformation solely, we see that this landscape is fuzzy because there are fine-grained categories of misinformation. You have rumor, you have fake news, you have hoax, you have satire, propaganda, conspiracy, right? So when you are exposed to these different types of misinformation, then it kind of becomes difficult because of the volume, because of the nature and nuanced language of the text. It becomes difficult to identify the intentions behind these messages. It becomes a non-trivial task. In my discussion, I would focus on the COVID-related misinformation. And we know how fast COVID has propagated throughout the globe. But the interesting fact is that not only that the virus has propagated or spread throughout the world, but also the COVID-related misinformation. They have risen very rapidly. A recent study shows that it focused on 4 different social networks, 4chan, Telegram, Gab, and Facebook, and it looked at the 2 months period of time, and it has noticed that how fast COVID-related misinformation has propagated across networks. It started with 4chan in December. Then within January and February, within 2 months of time, it has propagated through other networks via their hyperlinks. So the COVID-related misinformation has become viral. It has been produced in large volume. So we have this huge amount of information to process. And when you are overloaded with this amount of information, low quality information, you are in problem. And WHO has called this situation an infodemic. You have overabundance of information, low quality information. And it is very difficult to find trustworthy sources or reliable guidance in this infodemic. Now, the main problem with this infodemic is that it has caused serious social problems, serious social disruptions. It has caused death. People died because of believing in fake cure-based misinformation. There has been disruption and destruction to public property because of the conspiracy theory-based misinformation. So we just don't have an infodemic. We just don't have the problem of finding reliable guidance, but there are real harms to society. So the question is, how do we debunk the misinformation? How do we stop people propagating misinformation? How do we stop people believing in misinformation? Well, it's not very easy. It's not completely possible to stop people from spreading misinformation, right? So if we cannot stop people completely from spreading misinformation, what can we do? Pragmatically speaking, we can create effective strategies to at least flatten the curve of this infodemic. And if that is the goal, what would be the first step? The first step, I think, should be to detect misinformation. Okay, and this is a tall task. My interest is about the role of AI, how we can design AI solutions to detect misinformation in social networks, in social media. And I have three distinct goals. How do we do it efficiently, meaning using less resource? How do we do it effectively, meaning there should be less false negatives, there should be less false positives? And how do we do it rapidly? When misinformation propagates, when it emerges, when it propagates through the social media, it happens super fast. How do we cope up with that speed? Now, if we look at the landscape of artificial intelligence, if we see how it has evolved from the classical AI to modern AI, we will see that machine learning in general and deep learning in particular has provided us with very useful and powerful techniques to understand human language, to understand the intentions behind the text that we write. Right? But my question is, how matured are these solutions? How feasible are these solutions? How effective are these AI-based solutions? If you look at the AI-based detection techniques for identifying misinformation, we can divide that into two broad categories. The first category would be the source-based techniques, and the second category would be content-based technique. So let's look at the source-based technique. What the source-based approach does, it looks at a message. It could be a tweet, it could be a Facebook post, it could be a message anywhere, and then it would find the URL embedded into that message, and then would try to determine whether that URL points to a reliable source or not. So imagine that we have a machine learning classifier, and we have a set of labeled data. We have a set of tweets. In those tweets, we have URLs, and we know which URL points to a reliable source and which doesn't. The URLs that point to reliable source, we tag those tweets with true information tag, and the URLs that don't point to a reliable source, we will tag that as a misinformation. Then using those labeled tweets, we can train a machine learning classifier or a deep learning classifier, and then we can predict the intention of an unseen tweet by using this model. Right? So this type of approach solely rely on the URLs of the messages. But then this approach has limitations. The fundamental limitation is that if you have documents, if you have text or messages that doesn't have any tweet, this approach would not work. This approach would not work on any misinformation message that has a pointer to a reliable mainstream media. Or if that misinformation is propagated through a reliable mainstream media, this approach would not be able to identify that as a misinformation. The third limitation would be this. What if that misinformation is propagated by a very influential person, by individuals like the president of United States, or an unofficial source that has recently been emerged as a website? So you don't know whether that is reliable or not because that has just emerged. So it appears that the source-based approach is very limited in its efficacy. On the other hand, we have this content-based approach. In the content-based approach, what we do, we use natural language processing to understand the intentions behind the social media messages. NLP, as you can see, is a broad area. We are interested about the NLP that overlaps with AI. The NLP that the NLP models that we can develop with AI techniques. We will focus on this content-based approach of NLP and try to understand what are the strengths of this NLP-based approach, what are the limitations, what are the challenges, and what are the ways to move forward. So 3 things. First, a 30 seconds overview of the NLP in general. NLP is an interdisciplinary field of computer science and linguistics. The goal of NLP is to understand human language from speech and from text. So what NLP approaches try to do, imagine that you have an NLP system and you have a set of messages, right? You want to understand these messages. You want to determine the hidden intention behind these messages. To be able to process this text messages, the NLP system has to convert these texts into numbers, right? So the key component of any NLP system is to convert the text into numbers. Those numbers are the features. So each word in the text, these are features, and you want to convert those features into number features. So the first step towards building any NLP system is to be able to convert the text into numbers. And this is known as text embedding. The goal of text embedding is to somehow compress the text into numbers and retain the information hidden in the text. Now, we can do text embedding. There are trivial techniques to do text embedding. For instance, you can just use one-hot encoding. You create a vocabulary and then take a sentence and match the words in the sentence with the vocabulary words. If the word appears in the vocabulary, you put a 1 against that. And if the word doesn't appear in the vocabulary, then you put a 0, and so on and so forth. So essentially, you can encode your messages using one-hot encoding, 0s and 1s, just by comparing that with the vocabulary. Or you could just count the frequency, how many times a word appeared in a document, and use that count. But this simple count-based embedding technique is not very powerful because it doesn't consider the semantics of the language. It doesn't consider the syntactics of the language. It doesn't look at the context of the words. So the fundamental goal of text embeddings are threefold. We want to embed the text. We want to convert the text into numbers, because using those numbers, we want to make predictions about the intentions of the text messages. So in the text embedding, we want to capture the semantic relationship. For instance, if you embed these 2 words, Nebraska and Lincoln, you would like to convert these 2 words into numbers in such a fashion that Nebraska and Lincoln is somehow related, somehow closer. Or king and men are closer, queen and women are closer. We also want to capture syntactic relationships. So was and is, when they're converted into numbers, we want them to be closer. Had or has, they have to be closer as well. Contextual relationships. If you look at this sentence, the word sword has appeared multiple times, but in different contexts. We just don't want one embedding for one word, because one word might have multiple meanings depending on the context, depending on the sentence. So we want not just one embedding, but depending on the word, we want multiple embeddings of that word. So once you combine these 3 different aspects, the semantic relationships, the syntactic relationships, and contextual relationships, you end up having a language model. The tall task before NLP was to convert the text the language that is represented via text into numbers in such a fashion that the semantic, syntactic, and contextual relationships are encoded in that number space. And that would give us a very powerful language model. If we can have a powerful language model like this, then we should be able to use that for programmatic processing. The first big breakthrough, if you like, occurred with these two models, the word-to-vector and GloVe models. These two models were created to capture both the semantic relationships and the syntactic relationships in the text embedding, in the numbers. So word-to-vector came out in 2013 and GloVe came out in 2014. The main goal from high level of word-to-vector and GloVe was to take the words, the tokens, and then to convert those tokens into numbers. But while converting those tokens into numbers, the goal was to make sure that words that are semantically closer, words that are syntactically closer, remains closer into the embedded space. For example, king and men should be closer. Queen and women should be closer because they're semantically related. To capture this semantic affinity, to capture the syntactic affinity, what word-to-vector and GloVe model did, they looked at the co-occurrence information, how frequently one word would appear with another word or some other words. Looking at that frequency of co-occurrence, they would these two models would build the text embeddings. There's a slight difference between word-to-vector and GloVe. Word-to-vector is a predictive model, and GloVe is a count-based model. But the main goal of these two models is same: to capture the semantic relationship, to capture the syntactic relationship of the words. So as you can see, the words Spain and Madrid would be closer in that embedded space. Italy and Rome would be closer into that embedded space, right? So it's quite interesting that you are no more using the words, you're using the numbers, but the numbers carry the same information that the words would carry, right? One interesting, if you like, consequence of this conversion from text to numbers is that now you can use the numbers that represent the words and you can perform arithmetic operations on these words. For instance, if you look at take the embedding for king and deduct the embedding of man from the king, what you get is, if you like, kinghood. And then add the kinghood with a woman, then you get queen. So you see these words are represented by vectors. You are looking at the word, the vector king, the vector representation of man. You deduct man from king, so you get this king subtracted man vector. Then you add that king subtracted man vector, this yellow line, with the woman. And then with the rule of vector addition, you get the vector queen. So the beauty of this approach of text embedding is that we can now perform computation on the words, because words are no more words, these are numbers. But then the question is, how do we use these embeddings for detecting misinformation or analyzing text, understanding the intentions behind the text? Well, what we can do is this: we can take a very large general purpose corpus, all Wikipedia text, or some book corpus, which contains, the most frequently used words or most of the words that we use in our everyday life. In that corpus, we have the semantic relationship, every possible semantic relationship between the words that are contained over there, a syntactic relationship between the words that are contained over there. So you take that giant corpus and then you use that giant corpus to create word vectors, to create their embeddings. Once you have that giant set of embeddings, for each word you have their embeddings, it's a very large set, then you can take that large set of vectors to create a misinformation classifier. So imagine that this yellow box contains the embeddings. You take the embeddings, you take a tweet, the tweet has 10 words. For those 10 words, you know what are their embeddings. These are powerful embeddings. Then use those embeddings, use those numbers to feed it through a machine learning model, maybe a neural network, and then use that to train the model to predict whether it's a misinformation or not, whether it has positive sentiment or negative sentiment. You can extract entities, you can do translation and other NLP tasks. So two things that are relevant here. One, we have encoded a very general purpose, very large general purpose text corpus into a set of vectors. Each vector represents a word, and those vectors are very powerful. It's compact, but it contains the knowledge hidden in the language. It is kind of a proxy of the language model. And then we use that language model, then we use that encoded information in the numbers to create a misinformation classifier. But that did not solve the problem, because there are two reasons. Reason number one, these encoded vectors are not as powerful, because the way word-to-vector and love are created, they would only look at the co-occurrence information. They would look at the nearby words, right? So if two words are close by, then we would assume that they're related, and they would be encoded in the same vicinity in the number space, in the vector space, right? So you end up creating a not very deep model. That's limitation number one. Another limitation is that even though you train the word-to-vector model with a lot of words, for instance, the off-the-shelf word-to-vector model has been trained with 11 billion words. The off-the-shelf glove model was trained with the 2014 Wikipedia dump. These are very large. It's a super giant set of vectors representing millions of words. Even though we have these very large encoded words, but the main problem, other than being a shallow model, the main problem here is that these vectors don't capture the context of the words. For instance, think about the word head here. The word head can have different meaning depending on the context in which it has been used, right? The head could mean the head, a part of a body, head of a class, right? Trailhead, head as in mind, head as in ego, head as in sensibility, and so on and so forth. So when you use the same word in different contexts, the meaning of that word changes. The problem with word-to-vector and glove was that it would have just one embedding for one word, even though that word can be used in different contexts, in different sentences, and in those contexts, the same word would have different meaning. Word-to-vector and glove would not be able to understand that context. So it missed the polysemy, different meaning for the same word. So how do we overcome this challenge? How did we do it? Well, we overcome this challenge by creating a model that could not only capture the semantics, the syntactics, but also the context of the words. So the last part here, the contextual relationships, was needed to be encoded in the embeddings. And when you do that, you get the language model. So when I say language model, what I mean by this is following. Imagine that you have a sentence that has not been fully written. Based on the words that you have written, it should be able to compute the probability of the next word. It should be able to know what is the most likely word given the sequence of the words that you have just written. So if we wanted to have that kind of knowledge, because the next word depends on the context of the previous words. So unless you capture the context, you won't be able to make that kind of prediction. There are some very powerful and very useful models that has been developed along this line. For instance, ELMO, BERT, and GPT-3. And these models came up in last 2 years. So last 2 years, it appears that are very successful in terms of the advancement in NLP. So let's talk about the very first language model. It's called embeddings from language models. It came up in 2018. What ELMO did, it was able to not only capture the semantics and syntactics relationship, but also the contextual relationships of the words. The way it would do it, to embed a word, it would not just look at the surrounding words. It would look at the entire sentence preceding the word, and based on that, it would embed the next word. So if the same word appears in different places in the document, then it would have different embedding, because the preceding sentence to that word would be different. Thus, depending on the context, the embedding of the word would change. As a consequence, for the same word, we might have multiple embeddings. And that's how ELMO would capture the polysemy of the language. The implementation-wise, ELMO was based on a deep learning architecture. It is known as recurrent neural network. It is actually built by using a variant of RNN, which is known as LSTM, long short-term memory. ELMO used a bidirectional LSTM, and it trained that bidirectional LSTM on a specific task. And I don't want to go into the detail of this LSTM architecture. I want to give you a very high-level description of what ELMO did, or how it was implemented using this bidirectional LSTM. The bidirectional LSTM was trained on a very specific task. What was that task? A very simple task. Predict the next word based on a sequence of words. So using the first word, predict the next word. Using the first two words, predict the next word. Using the first three words of the sentence, predict the next word. But the cool thing about ELMO is that to create this model, to create the embeddings of the words, it not only looked at the previous sequence, to encode the next word, but it also looked at the post sequence. So take a word, look at the words before it, and look at the words after it. Take the sequence before it and take the sequence after it. So it would do the training. It would create two embeddings. One embedding in the forward direction, starting from I want N, you find the embedding for apple. And then using apple and want, you find the embedding for I, right? So you take a word, look at the prior sequence and look at the post sequence, you create two embeddings and then concatenate those two embeddings. Now you have a very powerful embedding of that word. So it appears that ELMO provided us with a very powerful language model. But the problem with ELMO was that to train ELMO with vast amounts of text, it was very expensive. Expensive in terms of computational resource, in terms of training time. One way that we could have used to make this computation much efficient by parallelizing this computation. So you deploy multiple hardwares and then you do the training, which was not possible with ELMO because of this recurrent neural network architecture. We cannot parallelize the training of recurrent neural network architectures. So people were looking for a more efficient solution that could be parallelized, and that could provide us even more powerful language model. So along that direction, along that goal, we invented this new model. It's known as BERT. It stands for Bidirectional Encoder Representations from Transformers. It came out in the same year, 2018. What BERT did is very simple. It got rid of the recurrent neural network. It used a simple feed-forward neural network, and that can be parallelized. That's one. And the other thing that it did, it used a masked language model. So if you take this sentence and if you put some mask on a randomly chosen words and train your neural network to predict that word, by forcing it to predict the word that are masked, you learn the embeddings better. You know those words, right? You know the word in this position. You know that it's went. You want this I to be able to predict the next word, and so on and so forth. So this masked language model turned out to be very powerful. It was based on another successful model. It's called Transformer. So there are multiple sophisticated components that are involved with the BERT-based solution. It appeared that BERT was very successful because we didn't have any recurrent connections, so we could train the BERT model using parallel hardware, so it was very efficient. And when BERT was trained with a giant text corpus, BERT model would become very powerful in terms of capturing the context, the syntax, and the semantics. The state-of-the-art BERT models were trained. There are two variants. There's a smaller version and there's a bigger version. The smaller version of the BERT was trained with 110 million parameters. It contains that many parameters. The larger BERT contains 340 million parameters. So when you have such big of an architecture, then you would require giant amount of text to train that model, and which was actually used to train the BERT model. To pre-train it, 800 million words were used from book corpus, and from Wikipedia, English Wikipedia, 2,500 million words were used, which gave us a very powerful language model, right? But then it required massive amounts of data and computation to train. But once you have done that training, once you have those off-shelf models, now you can use those off-shelf models to do classification, sentiment analysis, and those kind of tasks. But even so, BERT has some limitations. So one limitation that might impact the misinformation detection in online social network is that BERT might not be very effective on domains with distinctive linguistic characteristics. For instance, think about clinical domain. Think about the domain of scientific texts. So researchers have tried to use the vanilla BERT model on the clinical text and on the scientific text, and they found that BERT was not it was very good, but it was not the best. So what they had to do, they had to pre-train BERT using their domain-specific corpus. So you use the clinical text data to train the clinical BERT. You use the scientific text data to train the scientific BERT. And then those pre-trained clinical BERT or pre-trained scientific BERT would perform better than the vanilla BERT model, which tells us that BERT is super powerful, very efficient, but it has this domain-based limitation. So in summary, we see that the state-of-the-art approaches are very powerful in terms of capturing semantic, syntactic, contextual relationships. Once researchers were able to understand that, we could build powerful models by, increasing the capacity of the models and by training those models with large amount of text, then they have started looking into other improvements. A recent improvement was this GPT-3, Generative Pre-training Transformer model, which is 470 times bigger than the larger BERT. You have to remember that the larger BERT contained 340 million parameters. Multiply that with 470. You get a really very large model. And it's very powerful, actually. When you train it with a very giant text corpus, you get a very powerful language model. The good thing about this new language model, GPT-3, is that it doesn't require as much label training data for performing classification. So you want to classify misinformation, you don't have a lot of data, you could work with GPT-3, right? So we have looked at different text embedding techniques of MLP. We have seen that NLP is very successful in terms of creating text embedding, which can be used for performing classification and other NLP tasks. These embeddings are very powerful because it contains a model of the language, right? But even with these improvements or advancements of NLP-based approaches, do we have challenges in terms of detecting misinformation on social media messages? If so, what are those challenges? So now what we are going to do, we are going to look at some of the challenges of this NLP-based approaches. I have identified at least 4 challenges: scarcity of annotated data, diversity of misinformation, model transferability, and language understanding. So the scarcity of annotated data tells us that if you want to build a supervised ML model, even with those text embeddings, you need a supervised model. And for that supervised model, you need labeled data. So the tweets or Facebook messages that you have collected, you have to have tag for each of those messages. Whether those are misinformation or not, you need that tag. Using that tagged or labeled data, you will train your NLP model, machine learning model. So we need that labeled data. The problem is that labeling the data, the social media data, is very expensive because you have to perform fact checking, and that is expensive and time consuming. Another problem is that sometimes the claims are not always fully false or true. There are many messages that are very ambiguous. You wouldn't know whether they're spreading misinformation, the intention is to spread misinformation or not. Whether the message contains, a direct reference to misinformation or not, whether it's just a joke, it's very difficult to make a judgment on that. And this is very true about the COVID-related misinformation, because you get to find new type of misinformation, and that would emerge and spread very quickly. And that makes this data annotation problem very challenging in NLP. The second problem is the diversity of misinformation. Even though you can annotate the data, the problem is that there are fine-grained varieties of misinformation. A recent paper shows at least 17 different types of information, including false and true and misinformation, right? So when you have this large varieties and fine-grained classification, then creating a classifier becomes very challenging with this fine-grained categories and skewed data distribution. So that is another challenge. What if we have solved these 2 challenges? What if we don't have scarcity of annotated data? What if we don't have as much diversity in misinformation? Then are we good? Well, even though we are not good, even though we have solved those 2 problems, we are not good, because we have another issue. Imagine that you have trained a misinformation classifier using data that you collected from last December, January, and February. So your COVID model is event-specific. Events or chatter that has happened across those 3 months, you collected those data and created your model. And then you expect that model to make correct predictions on the new data that has emerged, let's say, after July, in September, October, November. Right? So you created one model, and you want to perform that model on a different data set. Well, that new data, the data that might have changed, that could have changed, that could be a new event. Maybe new conspiracy theory has emerged. new kind of misinformation has emerged, new type of threats have emerged, new kind of cures or suggestions to cures have emerged. The politics might have changed. Many things could have happened. So the model that you have created earlier, that might not be transferable, right? Another problem is that the false narratives, they emerge and propagate so fast because of our fear, because of the unknown, because of the uncertainty, they spread very quickly, right? And the social media adds fuel to this, the speed of propagation. And because of that, it's very difficult to create a generalizable model. It's very challenging to create a transferable model. But even if we can create a transferable model, we do have another problem. We do have the problem of effectiveness of that model, because we are not so sure if that model would be able to understand the language, even though it can understand the semantics, syntactics, and the context of the words. But would it be good for understanding the language? What I mean by this is the online discourses are nuanced. It's not just limited to positive and negative sentiment, right? And there's many falsehoods that don't have obvious sources, obvious intentions. So it's challenging to distinguish between what is misinformation and what is disinformation, given that we have fine-grained classes, we have mutually exclusive categories. And with this nuanced text, it's a big problem to understand the intention behind the messages. And if you think about it, the social media messages are very condensed. They contain allusions, indirect reference, irony, humor, and so on and so forth. They're highly compressed, right? And these messages are intentional. And when you have these highly compressed messages where intention is hidden in very deep, then you have this problem of decompressing it effectively. And you cannot just do that by using machine learning models that are only good at finding statistical regularities in the training data. Your ELMO, BERT, GPT-3, these models are very good, very powerful, but these are based on identifying statistical patterns in the training data, right? But for successful decompressing, we need something external. We need knowledge that is external to the training data. And that is kind of missing now. So in summary, we see that even though the NLP has advanced and evolved to a very matured stage, still it has challenges to cope with the COVID-related or online misinformation-related detection problem. But I'm an AI enthusiast. I have a big hope on AI. So what do I think about the future of AI in terms of coping the challenge of misinformation detection? Well, I wouldn't say that AI is the panacea. It is not. AI is not the solution here. But at least what I believe is the fact that AI has tremendous power. We can employ AI for social good. So in last, we don't have time here. So in last 2 minutes, I would like to give you a sketch, or if you like, an outline of a solution that AI can bring to at least detect misinformation, if not, with 100% effectiveness, but it could at least increase the current performance level. If you look at the social media messages, you would notice that the messages are multimodal, meaning the messages contain not only nuanced text, it contains URLs, it contains metadata, it contains geotags, hashtags, emojis, images, videos. So it contains multiple information sources. And each of these components, the information component, are very powerful, are very useful. They convey something very, very useful to us in terms of understanding the intentions behind a message. You may have a very short message, 160 character long message. It's very brief, very succinct, very concise, yet it contains so much information, maybe in different formats. Can we leverage this multimodal nature of of information hidden in the messages in social media, people have tried to look into this aspect. People have tried to look at this multimodal and hierarchical, multi-layered nature of information content that we have in the social media messages. And by leveraging these different information sources, maybe we can improve the current performance level. So here is my sketch for a hybrid model. I would anticipate that the hybrid model would be based on multiple components. It would have the source-based approach, so we could employ deep learning technique for analyzing the source that is associated with, for instance, a tweet. You have a URL, we can parse that using deep learning model and understand the intentions behind that, that tweet that has the embedded URL. We can use text-based approach. So for transferability purpose, we can use NLP for extracting generalized features. So in terms of finding the pattern that are event specific, we can find patterns that are not event specific, that are more general. So you can train an NLP model based on one event data, but that can be applied, on the data that has that is based on new event. So it would increase the generalizability of the NLP model, and then we could add some kind of knowledge graph, encode external knowledge with that NLP system. We can also mine the non-text data. For instance, we could look at the images, the videos, and then we could use deep learning, the solutions that are very powerful for image classification, image recognition, video processing. We could use that as well. And finally, since we have the metadata associated with the messages, we could look at the graph properties of these messages. And people have done that. There are a lot of work that has been done along that direction. So for each of these components, people have worked in isolation, but it's a very good strategy to combine these different approaches and kind of create a hybrid model that would take us beyond this positive negative sentiment analysis based system that we currently have. Misinformation is complex. It's nuanced. It's beyond positive and negative sentiments. A misinformation message can have positive sentiment. A true information message can have high negative sentiment. So it's not a simple binary classification problem. It's beyond that. It's not just a text classification problem. It's not just a URL classification problem. It's not just an image classification problem. It's not just a graph theoretic analysis problem. It's a combination of many things. And maybe it's a good idea to combine these different, very powerful research that we have done so far and have a better hybrid model. Well, I think that's it. Thank you very much. I'll take questions if you have any.
So there were a few questions in the chat. I'm starting at the bottom here. With the, let's see here. With the multimodal strategy, have you looked at the replies to a given tweet to leverage the online response to potential misinformation? It seems like replies are most normally in agreement or disagreement with the original post.
Yeah, so in my research, a very good question. In my research, so the recent work that I have done, we have collected tweets and the replies, and we have separately analyzed the tweets, build a model just based on the source tweets, and then build another model just with the reply tweets. And then created the third model that combined the source tweet and the reply tweet, right? In general, what we have found is that the reply tweets are a very good indicator of the hidden intentions behind the tweets. So in terms of identifying misinformation, reply tweets are very, very useful.
Another question was, so how close are we to having an AI that can identify disinformation or misinformation on social media that is addressed to the common man?
So in terms of identifying disinformation, which are deliberately created to cause harm, people have done very good work in terms of identifying bots, cyborgs. So we have done some very good work in that in that area. But identifying misinformation in real time, we are still far behind that. You will find different systems that can identify, emotions behind these messages, or they would just look at the URLs, to identify the misinformation in the messages or not. But beyond that, we don't have a very good content-based real-time misinformation detector, and we are far behind that now.
Once the AI filter is created, how do we establish trust in the model by the users?
That is the next question. So in my talk, I did not talk at all about our problem. There are two main problems. One problem, the apps that we use, they're designed to hook you, to be attached to those, to click on whatever you see, to share that. That's one problem, algorithmic problem. Another problem is that our unconscious biases, right? So that's a broader issue, and I didn't go into that. Maybe that's a discussion for another day.
Okay. The next one is how to develop AI to handle language code that is not part of natural language. An example that was given, such as the use of the word pasta that may indicate self-harm.
That adds another layer of complexity of what I have just been discussing. That makes things worse than what we have now. Yeah.
Okay. And I think this is the last one. So there was anti-maskers in Omaha are planning a protest at Hy-Vee shopping without masks, claiming the U.S. constitutional right and support from their medical experts. How would you counter their logic and or legal standing in this case with AI?
We can't. Unfortunately, we can't. The problem is twofold here. Problem number one, how do you first of all identify their intention, real intention, programmatically, without involving any human being? That is the most non-trivial thing to do. And then the next thing is, how do you prevent them from doing that? That is even more harder than identification. So I would not say that we are very hopeful. We don't expect to have a very good, effective solution in near future. It's a challenging problem. That's why the title of my talk is The Challenges of AI. We have not conquered it yet. It's difficult, but we are working hard.
Those are all of the questions that were in the chat, unless someone else has one. I'll just remind everybody, I've put it in the chat a few times, but if you haven't done so already, if you can fill out our session survey just to give us feedback, that helps us make conferences better all the time. So we value that. And thank you very much, Mohammed. This was a great presentation.
Yeah, sure. Thank you.